So we are going to this is the last segment we have for the lectures on features. And last time we were talking about SIFT features, so we'll finish that segment today. And I think that's the last segment for this lecture. So we were talking about, so we went through what is like the overall approach we have for extracting SIFT features, and what were all the different characteristics of this kind of feature. So in SIFT, what we do is we try to first identify the key point locations, or you can say like interesting point locations. And to do that, we look into like blob kind of structure. Okay, and to detect these blobs, we have this Laplacian of Gaussian kernel. And again, it's a very basic filtering operation. So during filtering, you just use this kernel and see if this kind of pattern is present in your input image or not. And you say that, okay, that's like the interesting point which you are actually looking for. And you do that at multiple scales. And again, the idea is like if the scale of your image is actually varying, then this will make your algorithm scale invariant. Now, this is I will say is the core of SIFT algorithm. And this slide actually tells you exactly how the SIFT features are extracted. Okay, so I think we briefly went over this again. Let me do a quick recap of this. This is your input image, and these are like all the kernels at different scales. And you, as you know, like we discussed last time, this kernel is actually Laplacian of Gaussian, which you can also say like double derivative of Gaussian. And what you do is to define these kernels. So when you're taking the derivative, the Gaussian function you will use, that will have actually different kind of standard deviations. Okay, so you're kind of increasing the standard deviation for a Gaussian function to obtain these kernels. And then again, you perform filtering using these Gaussian kernels on the input image. And it's going to detect like, you can say like these are, you can say interesting points, but mostly we are looking edges here. And again, we are detecting that at different scales. Okay, so that's like the initial step. Now the crux is how exactly we determine whether like a pixel location is a key point or not. Okay, so what you do, so whatever step I'm going to explain, you will repeat that step for all the pixels on all these heat maps, which are coming from different scales. Okay, so we'll just discuss one pixel location, but you will repeat that for all the locations. Okay, so let's say we are interested in this scale, which is the 4th scale. So we will take this heat map, and again, this is just showing like you the grid formation, or you can select grid format for the same heat map. Now, let's say we are looking at this pixel location. What we'll do is we will try to look the activations of the neighboring pixel locations. Okay, so all the green ones. And while we do so, what we do is we look the neighbors which are in the current scale. So exactly this heat map. In addition to that, we also look into like the other scales. Let's say the scale which is greater than this one, and the scale which is less than this one. All right, so these two. So these are the pixels, the neighboring pixels, okay, the green ones, and this is coming from 5th scale. So again, what we do, so these are like all the neighbors of this pixel. And similarly, you'll have neighbors for all the pixels in all these 4 or 5 heat maps, right? So for each pixel, you will see if it's a maximum or not, okay, or it's minimum or not. If it's maximum or minimum, you will say that that's your key point, and that's what you are interested in. And you will just record like the XY location of that pixel. And you will also record like from which scale it was coming. For example, for this pixel, if it is like, let's say maximum or minimum, we'll have XY location for this pixel, and we'll have scale as 4. That's the 3rd parameter. And this is like all we need. So similarly, we'll collect like, we will collect all the key points in these different key maps. And then that will be a long list whenever we find like a maximum or minimum. And then you say that, okay, these are your set of key points. So that's how we determine key points in SIFT algorithm. And this was something interesting. Instead of computing double derivative for your filter, what you can do is you can actually approximate that using difference of Gaussian. So we discussed this briefly last time. If you have two Gaussian kernels with different standard deviation, you can actually just subtract those two Gaussians. And that difference is going to give you a function which looks exactly like inverted Mexican hat, which is your Laplacian of Gaussian function. Okay, so you don't have to compute derivatives, which is kind of expensive because you have multiplication operation there. Instead, you just compute difference of Gaussian, which is computationally cheaper than multiplication.